Yeah, so today I'm going to be talking about how to prevent like polarization in social networks based on algorithmic recommendation algorithms, AI-based recommendation algorithms. This is joint work with Professor Christian Borges, Jennifer Chase, and Ellen Pickosick. So to motivate why this is important, social networks are like one of the largest, like most important ways in which we conduct a lot of things in society today. It's the primary way in which we get information, the way we communicate with others, the way we get access to new ideas, the way we build communities. It's also important for like mental health and mental health tips, and also for like online democracy and things like that. Social media has really played a large role in like shaping these things in today's society. However, the large internet platforms who own these social media companies, their profit is gained from engagement. And this doesn't necessarily lead to the best incentives for them when it compared to the users, because they get their profit just from like showing content, and so they often just show them as addictive content, not necessarily the healthiest content for people on the platform. In addition, they often use AI-based recommender algorithms, and these are good for a variety of reasons. For example, there's huge amount of content, even like with like music streaming or things like that, and these algorithms help to curate and like filter without needing a human to like do this manually for everyone, and like which helps us personalize, discover similar content, no matter how niche, no matter how obscure. By using these like AI algorithms, we can still curate and help people without necessarily requiring a lot of work. It's also very important for like community building around similar interests and like self-discovery and a bunch of very important things that they use. However, these recommender algorithms have been documented to have a bunch of adverse effects. For example, they often lead to polarization because of the feedback loops created by these networks can often draw people apart when we're trying to bring them together. They also, for example, can have a very negative effect on minorities. Papers have shown that, for example, like in LinkedIn and stuff like that, by using names, it might limit how their jobs are exposed. They might not show them as good of like job recommendations, which create like algorithmic glass ceilings, not just the glass ceilings that we see in real life. In addition, it's been documented that because of these effects, these AI-based recommender algorithms disproportionately spread disinformation and propaganda to like minority groups. And so there's all these adverse effects, and the main one we're going to be trying to tackle today is the idea of polarization and filter bubbles. And so the main question is, can we design content recommendation algorithms that preserve the positive aspects? That's that curation, that like self-discovery, those like similar interests, without avoiding the pitfalls of filter bubbles, polarization, and some of those other more negative effects. And so to do this, we model the platform and the users using a standard multi-banded formulation from computer science. And basically the way a banded formulation works is that there's K categories or arms, which is like based on like the original kind of like idea behind linking up arms. Like you get at a lottery and you're pulling arms and you get some kind of like reward, some kind of random reward. But in this context, the K categories are like basic kinds of content to show the users. E.g. could be fashion, sports, left-leaning political content, right-leaning political content. And then we have end users on the platform. And so for each user, they have a certain like preference, which we model as like a probability distribution with a random reward. And so each time the platform pulls the arm, which is basically show them content from that category, they get some kind of random reward, which could be measured like by ad revenue, time watch, clicks, etc. However you want to actually model this in the real world, is just some kind of random reward that kind of varies around some mean. And then the goal of the platform is that every time step, which could be like days, every time they log in, you show a user some kind of content, and based on some distribution that you have a priori, because they're often like random, the algorithms are usually random, they didn't just show them the same thing every time. And they get some reward, the platform, and their goal is to maximize the amount of reward the platform gets over the whole time series. So they'll be like small t. And to make this more concrete, using like more mathematical terms, we're saying that for each user in the n, like square n is just like the group of all users, there's, for each arm j, there exists some reward distribution which is unknown to the platform, duj, where mu uj denotes the average rewards for user u when you show them category j. So basically this is saying that, okay, let's say like we're talking about like watching films, for example, maybe they like horror films versus like animation films, but they're not gonna like every horror film the same and every animation film the same. So there's kind of like a reward, like a randomness to like what you get from that. But still, they might still have like an expected like preference that's better for horror films versus like animation. And so mu j denotes that like kind of like baseline preference, but there'll still be some variance around this. And so at every time step t, the platform decides the probability distribution, basically like what is the probability of showing user u content from category j. And that's like given by this vector pu for each user, and each of the components of the vector denotes the probability distribution of the probability of picking that content for that user. And so each time step t, the platform samples from this distribution and picks an arm j u t for each user, and then receives a reward, which we're going to call x u t, which is distributed according to that like preference distribution. And just to like tie that in, so we're saying that the expected value of this reward, this random reward, is given by that mu jut that we mentioned earlier. And so therefore, the platform's objective is to maximize this this function, the last one, the expected value. This is their objective function, and their goal is to maximize this this function. And so so looking at this problem in the standard multi-arm Barnett formulations, what ends up happening is that at first the platform doesn't know what the user does, so they just kind of show them whatever, and eventually they pick and they learn what's better, and then eventually these algorithms converge to just picking one arm all the time to show the user, because that's the thing they see gets the most engagement. And so, and that's what leads to these filter bubbles and this like kind of like disjoint polarization gaps, because you're persistently showing them just the same thing over and over again, well, the same category over and over again. So the intuition behind how you might want to prevent polarization of filter bubbles is that you want to say that the content that is shown to each user is not too far from other users on the platform. And so a simple way to enforce this is to say that each user is showing content that is close to the average content that you show other users. That's like a naive way that you might first think of like formulating this problem. And then more technically, let p average denote the average content distribution of all users, where we're taking average over the vector. And then we impose a constraint saying that basically the distance between the probability distribution for each user is close to the average by some kind of polarization like allowance or personalization allowance, which we call delta, where delta leaves in 0, 1, and we impose this constraint at every time step. So if we let p star be the optimal policy on this constraint, that is the policy that maximizes this objective function, however, subject to the constraint that what you show people can be too far apart, can be more far apart than this delta. We call that policy p star u, where there's going to be an optimal policy for each user. And so so you might think that might be a good formulation that's going to achieve what we want to do. Okay, let's go home, polarization solved. However, doing it that way has some unintended adverse effects. Basically, the effect is that in reality, when you actually solve what these distributions look like, these p stars look like, the cost of diversification is mostly borne by the minority groups. Basically, what happens, this lemma shows like basically what happens that for people who are in the majority group, they basically still see just what they like and nothing else. And only people who are seeing diverse content are people who are in the smaller group. And this is just a consequence of how we formulated the problem. And so you might want to, so that is now creating what we call tyranny of the majority, where the cost of diversification, even though like, yes, the whole platform has more diversity, but where is this diversity coming from? It's just by showing minorities things they don't like, while the people who are like the majority of the platform still get to see what they like and nothing else. And so we might want to have a more equitable approach to like solving this problem. And so that's what led us to our approach. And the intuition behind this approach is that users should still be only seeing content that they like. So you don't want to be showing people this stuff that they don't like, which kind of avoids this tyranny of the majority problem. However, the content that someone sees must contain like some flavor, some sample of what everyone else in the whole platform likes. And that's like thus that avoids the filter bubbles problem, but we're still showing them what they like. And so basically the constraints should be like kind of geared towards what the platform, what the interests of the users are. And so this is what led us to our approaches to solving this problem. So the first approach is what we call the polarization cap approach. So basically, we have this gamma parameter, which basically serves as like how much personalization can you actually show users. And the way we mathematically formulate this is that we say that component-wise, the amount of probability you place on each content should be at least gamma times the average of everyone else. So basically it's kind of a soft floor, and it kind of is a floor on the amount you show, so you have to show a little bit of what everyone else is seeing, based on how much everyone else is seeing that. And this is for all users, not just for any particular user. And so this gamma parameter serves as a cap on the level of personalization. So basically when gamma is 0, this is basically no constraint. You're basically allowed to do anything that you want. But when gamma is 1, we're saying that everyone has to equal the average, which means everyone has to be shown the exact same distribution. And so gamma helps you, like, lets you control how much you value showing like the diversity of content. And under this formulation, we prove that for regimes where gamma is less than half, this does what you want. Basically, everyone sees more content, but they still see mostly what they like, but everyone still sees a more diverse content. And so this kind of this approach solves our problem of preventing the filter bubbles without forcing anyone to see stuff they don't want, and the burden of diversification is more equally spread across all the different groups within the platform, different interest groups. Then a second approach we have is, instead of necessarily, maybe the regulator doesn't necessarily want to have this hard cap, this hard constraint on the probability distributions. They want something a little bit softer, which allows the platform to kind of decide what they want. And so what you can do is you can either do like a tax on personalization, and basically the platform has the choice to pay this tax if they think it's worth it to still show people what they want. Or you can even think of it as a credit where you give people like incentives to like show more diverse content. And so the way we model this is we have this this penalty function, Ri, and looking more into what this is saying. So this here is just that p average, for just more written out, expanded out. Basically we say that, so here this is saying how much more are you showing someone more stuff than the average. Less than the average. If you're showing them less than, so if you go back to that old one where we had the gamma p average, if you're going below that, that's what this is formulating. If you're going above, if you're showing more than the average, that's fine. So we take the max between those. So basically we're only penalizing you when we're showing less than what we kind of, the hard constraint we had before. And then we have this, and this is across all arms, because we broke this out instead of having the vector-wise component, so we add this across all the different categories that you show. And then this eta variable is kind of saying like, how strongly do you want to tax, or how strongly do you want to subsidize the platform based on this, based on when they violate the constraints from earlier on. If you know like it's kind of like a Laplacian Lagrangian type thing. And then, so basically when eta is greater than 0, this is a tax, and when eta is less than 0, so when it's negative, it's a subsidy. And basically eta, not only the magnitude of eta tells you how much you want to penalize or subsidize, and the sign of eta tells you whether it's a credit or a tax. And this is like the second formulation. So basically, the platform wants to maximize a slightly different objective function where it's basically that expected reward minus this penalty from violating the constraints. And so our main results are that under both formulations, we design and show that there are algorithms that are efficient at content recommendation while learning, because in all these examples, the platform doesn't actually know the user's preferences, but they have to like learn the preferences while also showing and getting the rewards that they like, and you're kind of like simultaneously balancing between learning the true distributions and showing good content. So you want to learn in a good way. And so we show that there are algorithms that are optimal in terms of like balancing this trade-off between learning and content recommendation. And we also show that the algorithms we come up with are the best possible algorithms that you can get under this problem formulation. That is, there's no algorithm that does better at balancing this trade-off of maximizing the reward while still learning efficiently. And those are our main results. And so in conclusion, this work proposes a flexible approach to disincentivizing filter bubbles and polarization that adapt to the interests of the individuals in the network. It comes out in a more natural way without necessarily having the regulator like fixing anything that they don't know. And we also show that our model incentivizes diversity in a way that is more equitable to users on the platform and is also a scalable, nearly optimal algorithm for learning and recommending content under our framework.